So we'll pick up where we left off. Just to orient you in terms of where we are in day 3, where we'll conclude the discussion of the history, structure, bonding, electron counting, these sorts of things today. And then we'll have 3 lectures that explore the fundamental elementary steps that organometallic complexes can participate in. And where any of these start and stop is not that important. So I think by the time we get to day 7, then we'll try to basically have 1 topic per day, but there's a lot of bleed over in these early lectures. So if it seems like we're running ahead or behind, well, we never run ahead, but if it seems like we're running too far behind, then there's some built-in time for this, so that's fine. So let's pick up where we left off, and that was in finishing the discussion of electron counting. So let me share my iPad here. We had finished last class with the discussion of hapticity and how haptotropic shifts, which are changes between 2 haptotropic states, for example, eta 1 and eta 3, how those can lead to changes in overall electron count as well as the coordination number. And now we'll jump into some more exotic types of ligand structures that you may encounter, although some of these are not actually that exotic, they're reasonably commonplace. Before doing that, I want to ask if there are any questions for clarification from the previous lecture or any of the problems that we've worked on so far. Okay, well, feel free at any time to raise your hand or interrupt if anything's unclear. Some of this, I think, will be reviewed at people who've seen this before, others as completely new, so there's naturally going to be different paces at which you know, you're able to digest the material, and that's okay. That's part and parcel for these types of grad courses. So let's talk about bridging. This is a phenomenon that's exhibited by several different classes of ligands, notably halides, alkoxides, hydrides, as well as carbonyl compounds, to name just a few. And we talked about this nomenclature of bridging before, the mu Greek letter, and then the number that's in superscript denotes the number of metals bridged by that ligand. So let's first consider the case of chloride as a bridging ligand. And one way that I like to think about it is in terms of the electron counting. I like to think about it as if the chloride ligand is an X-type donor to one of the metals that it's bridging and an L-type donor to the other metal that it's bridging. And this often works out because typically bridging, not always, but typically bridging elements come in pairs. So you can count one as X-type to one metal and the second as X-type to the second metal, and the overall charge and electron counting will work just fine. So I've got that, I have that denoted here, where the bridging chloride would be X-type with respect to the metal on the right and L-type with respect to the metal on the left. And you could also draw that now without the lone pair representation shown here. And in point of fact, again, this is bookkeeping. So you could draw it the opposite way, and that should be equivalent in terms of your overall electron counting. If it's not, then you have to take a step back excuse me, and reconsider what you're doing. Another similar case is that of the bridging hydride. Now, this one is a little bit different because, at least to me, it's harder to visualize because you don't have the benefit of these lone pair electrons that naturally look like they could form another interaction with the metal. In this case, we consider that this sigma bond between one metal and the next is actually essentially the L-type donor. So that filled sigma bond is now donating electron density to the other metal, or at least that's one way to think about it. So these representations shown here, again, are all equivalent. So the overall electron counting should work out whether you, irrespective of how you count it, as long as you get to a maximally symmetric structure at the end. That will be clearer in a moment. And so then in terms of the electron counting, as I said, if we consider the case of halide, it's X type with respect to one metal, L type with respect to the other. And in either case, we count it as two electrons or one electron pair per metal. Likewise with hydride. Now the case is slightly different when it comes to bridging carbonyl. Much of the analysis is the same, but in terms of the overall electron counting, we count it as just one electron per metal. And you'll find if you don't do this, you'll get to some weird and wacky numbers. And so if you misremember this and you start getting odd electron counts or things like that, then you have to consider that maybe you're framing this. And this doesn't necessarily fall out of first principles. Again, electron counting is ultimately about accounting, and it's a formalism. But this has to do with the fact that unlike chloride, unlike hydride, which are charged bridging ligands, the carbonyl is a neutral bridging ligand. So you can't overcount the number of electrons that are involved in bonding. And that's what you would do if you counted it as 2 electrons per minute. So we can consider this example. I said bridging halides often come in pairs, but here's a counter example to that rule, that of this tris chloro mu2 bis ruthenium complex. And you see in terms of how we would represent this in a molecular formula, we would say mu2, chloride, 3 of them, and then in this case, 6 phosphine ligands. And the overall charge is 1 here. So now we'll consider how to count metal-metal bonds and also how to predict from a given formula how many metal-metal bonds you might expect. And I think a general rule of thumb here is that if you get to an overall odd electron count, let's say you do the end of your electron counting and it's 17 electron or something like that, often these odd electron count species will try to form a metal-metal bond to get to what will end up being an even electron count species, because metal complexes, just like main group elements, prefer to be in the closed shell if possible. So there is a formula here that can allow you to predict the number of metal-metal bonds, and we'll walk through a specific example here, which is you count the number of metals, and that will be this variable m. You count the total number of valence electrons, which will be the variable e, and then you multiply m by 18, again, following the 18 electron rule. You subtract the total number of valence electrons and divide by 2, and that will give you the number of metal bonds. So let's look at a specific example. Oh, let me add one more note here, which is that metal-metal bond, in terms of electron counting, metal-metal bonds count for 1 valence electron per metal. Okay, so let's consider the case of cobalt-2 CO8. And we can just plug right into this formula here. We've got 2 metals. We see that we only have CO ligands, so we don't have any charge to account for. Cobalt is a D wet metal. D9, cobalt 0 should be D9, cobalt, I think someone said D7, cobalt plus 2 would be D7. So, and we have 8 CO ligands, each of which is going to donate 2 electrons. So we can just do the math here. 8 times 2 electrons from the ligand plus 2 times 9 electrons from the metal, and that's going to get to, we can do our early morning math, 34 electrons, which would be equal to N. So now we can plug directly in this formula, and then we have 18 times the number of metals minus the number of valence electrons divided by 2, and that will predict one metal-metal bond. And so what might that look like then? We can just build it from the inside out here, knowing that we have a metal-metal bond to account for. And conveniently enough, we have 8 CO ligands, nicely symmetric structure. Sorry, it's always confusing when you have cobalt carbonyl because I end up drawing them as if they all look the same. And as it turns out, this example is in point of fact more complex than it looks at first glance, because the species drawn here actually can exist in equilibrium, bless you, with a form that is CO bridged. And that was characterized in this you might not guess that from first principles, but that was characterized in this inorganic chemistry paper cited here. And so this is an example not only of the metal-metal bonding, but also of the bridging carbonyls. And I'll leave it to you to as a homework exercise, think through the electron counting in both of these situations, noting that there's no change in oxidation state in terms of this this isomerization process. Okay, so let's go ahead and turn things over to wrap up the problems of the day from last class period, which are centered on electron counting. So a good way to warm up your brain in the early morning. So we'll go ahead and just go right through problem of the day number 3 and problem of the day number 4. So take a minute and think through both of those problems. So problem of the day number 3 asks you to consider a reaction between nickel cod, nickel bis cyclooctadiene, shown on the left, which is an archetypal nickel 0 complex, as well as nickel dichloride glyme, a complex shown on the right, which is a common nickel 2 halide salt, in the presence of the ligand Iper. And maybe just to kickstart things before giving everyone a chance to think about it on their own, can somebody tell me what the structure of Iper is?
This diisopropyl imidazole.
Okay, and saturated or unsaturated backbone?
It's not an acid FDR, so it's unsaturated. And then you have like,
it is unsaturated, right? Okay.
We need to ship this.
You know, when I was recording this by myself, this was my main fear, that I would just be on the exact wrong screen share the whole time. And actually, I haven't gone back yet to check if I did that. So I very well may have. So Philip said that the structure here is it's this. We'll get to carbines in a subsequent lecture. So if you're looking at this, like what is going on here, then that's fine. Bis 2,6-diisopropyl phenyl. Imidazole. And so the nomenclature here, it takes a little getting used to, but it then becomes pretty intuitive. Most of the common NHCs follow a system whereby the first part of the name, in this case, I, refers to whether the backbone is saturated or unsaturated. So in the case of Si, you have a saturated backbone with CH2, CH2. In the case of I, you have an unsaturated backbone. And then the second part of the name denotes the substituents off of nitrogen. So PR in this case is an abbreviation for the dip group that we've encountered before in class, this 2,6-diisopropyl. Okay, so now we've got the ligand structure drawn up, so everyone can take a stab at this, hopefully. And then I'll just go ahead as you're thinking about that and preview problem of the day number 4 as well, which is an electron counting exercise. It asks you to provide the coordination number, metal oxidation state, d-electron count, and overall electron count for these 3 complexes shown. And I think in general, in terms of trickiness, it's probably organized left to right in increasing trickiness. So start on the left if you're wanting to get oriented. Oh, and I also should add that problem of the day number 3 also had an electron counting component. So we did problem part A together, which was the structure of the dip. We need to then account for problem part B, which is to predict the structure of the major product. Part C, which is to provide the term for this reaction, and then part D, which is the electron counting part, metal number, oxidation state, the electron count, and overall electron count you could do all of them, but before the product specifically. Okay, so take a minute to think that through on your own, and then a minute as well to discuss with a neighbor and compare notes, and then we'll reconvene as a class to go through it. As always, please feel free to compare with your neighbor. Okay, let's take a stab at B and C. Those go together. What do you think, Chayu? Do you prefer Chayu or Jenny? Both, fine. Okay, Chayu, what do you think?
For like nickel bond.
Okay. That looks reasonable. Two mu2 chloros.
Also with the carbene aside from two.
Carbene. One or two per metal? One per metal. Okay. I will draw the whole structure since it's defined below. Okay, and what would the oxidation state of nickel be in this structure? Two. Nickel one. Okay, so let's say this is nickel one dimer. And the overall process then here, we go from a nickel 0 complex, a nickel 2 complex, and we get to a bis nickel 1 complex, which is called what? What do you think, Jenny? You're not sure? What is the name of this redox process where you would go from nickel 0 plus nickel 2 to two equivalents of nickel 1? Assist from the audience, anyone? Which proportionation? Comproportionation. Okay, I always get these mixed up myself. There's comproportionation, which is this process, and disproportionation, which is the opposite process, to metals, the same oxidation state going to lower and higher oxidation state species. Perfect. And then the last part, how about Pranali?
What's the question?
The coordination number, metal oxidation state, d electron count, and overall electron count for the complex. We got a head start because we have the oxidation state as nickel 1. So that's good.
Coordination.
Coordination number, I think we can say is 4. This is again one of these cases. Do you like to count the metal-metal bond or not count the metal-metal? We'll count it. So we'll say coordination number 4. Because that counts as an electron pair involved in bonding. What about the oxidation state? We said is +1. Now the d electron count. Pull out your mental periodic table or on your phone. So nickel is in which column? And then nickel +1 would be what?
Nickel +1 would be 7.
9, okay. 9. And lastly, the overall electron count per metal.
So we have 9 chlorides, which would be 2 electrons each. 4.
Yeah.
Yeah.
And we haven't talked about electron counting for the NHC. So if this looks unfamiliar, I'll just give you a hint that it's going to be like an L-type ligand. So it will be 2 electrons. So you said 4 plus these 2. So we have 6 electrons from the ligands. And then the metal-metal bond we count as 1 electron. And then put it all together, and we have anybody get anything different from that? And this particular nickel 1 dimer complex, yeah, great job to all of the volunteers. Thank you very much. Fantastic. Was first reported by the lab of Matt Sigman in this 2015 inorganic chemistry paper, but has found widespread use in catalysis, which is highlighted in this review by our chemist of the day, who some may recognize. Anybody? Day 2 chemist of the day. I reshare that in case you want to photo. Day 2 chemist of the day is Wenji said, MJ Ko from the US, National University of Singapore. Did his graduate and postdoc training with Amir Hobeda and Dick Schrock, and then started his independent career. He's used this dimer complex, as has the likes of Franziska Schoenebeck and others, for alkene isomerization, alkene hydrofunctionalization, and alkene difunctionalization, transformations that are near and dear to our hearts. Engle. Wonderful. Okay, let's proceed forward to problem of the day number 4. So more electron counting practice. What do you say there, Jared, for the leftmost complex?
Coordinate. Is it called 8? Does the ring at the top now is 3?
Yep, based on the how we are defining to do coordination number, we would say this has, what did you say, 8? That's right, 8. Okay. Oxidation state.
Is it going to be tungsten 4?
How did you get there?
Tungsten was made of, so that D6, and then the 2 chlorides and the ring on top would be 3 negative, and it's positively charged, so 4, I think.
Yeah, so we don't even need to consider the electron count of the metal to get the oxidation state. I think you hit it right on the head, which is, let's just count the different X-type ligands. So we have chloride as an X-type ligand, 2 of them. We have the CP as an X-type ligand. And we have an overall charge, which you nicely counted for, of +1. So that means that however much charge the ligands add up to, we're going to need one more charge than that to be at this overall +1 charge. So I think you correctly said +4 oxidation state at tungsten. And then I think you took it one step further to say that tungsten was D what? Tungsten 0 is D6, so tungsten +4 will be D2. And then the overall electron count, putting all of this together, you've got a D2 metal. You've got 2 X-type ligands. Maybe we'll just do this one in a little bit more detail. The others we can potentially do a little faster. So we have a D2 metal. We have 2 chlorides, which are X-type. Two phosphines, L-type, 3 phosphines, excuse me, L-type, and then the CP, which we said is X2L type. Okay, so let's put all this together. 2 electron count from D2, 2 X-type ligands is how many total, Jared? 4. 3 L-type will be how many? 6, and then 1 X2L type will be
6 again.
6 again, for overall 18 electrons. Any questions on that one? Beautiful, Jared. Okay, middle one now. We'll do this one just a little bit more quickly. Jayloon, what do you think for this one?
16.
Okay, first the coordination number. 3 plus 3 plus, how many is the owl going to be based on our definition?
Or what?
The coordination number, you have 3 from one CP, 3 from another CP, and then
2 from the
2 from the owl. So that would be 8 total. Oxidation state is 4. Tell us how you got there.
2 from the 1 from the plus and 2 from the CP rings and 1 from the LP.
From the owl. This is not a note that that's not a alkene. It's a owl ligand, which is important. Perfect. Which gives us D what? Okay. Zirconium. Metallic zirconium is D4, and we've got +4 oxidation state. That will get us D0. And then the overall electron count here is what?
16.
Okay, last and perhaps most puzzling or most mysterious of the 3, let's consider this one. Alex, walk us through your thinking on this one.
So it's like nickel 0.
Well, let's first do the coordination number, which itself is going to be a little awkward to do. So let's count the unambiguous ones first, which are the 3 alkene ligands.
It's 3. Okay. So that's going to be 3. And then are you counting the, I guess if you count the metal-metal bond, it's going to be 5.
Right. These are that example like we talked about of Z-type ligands, right? Where you have a Lewis acid, in this case, lithium +1, accepting electrons from a filled d orbital on the metal. This is again a case where coordination number is a little bit ambiguous, so we'll just write both. So if you choose to count those, then you would count as 5. If you don't, then you would count 3. So how about the overall oxidation state here? Let's just try to charge balance. So the COD ligands, are they bringing any charge?
The only charge is from the lithium. So
Okay.
nickel's either in negative oxidation state or it's 0. So
Okay, so how would you get to a charge neutral complex here?
you either need counter anions or nickel is -2
Okay,
oxidation.
there are no counter ions. So then you're saying that we'll get to a -2 oxidation state at nickel. Does that make you uncomfortable, Alex?
Well, I've read a little bit of Max Palkowitz's negative oxidations group meeting. So yes, but no.
Okay. You're comfortable with your discomfort. And so let's now just assume that we're on the right track here and we have this negative oxidation state. So what does that give us in terms of the electron count then?
12.
And then the overall electron count.
So we'll get 6 from the olefins. Yes, using the formalism from earlier, another 2 total for the metal-metal bonds, 1 per.
Well, these are not, I wouldn't bin these as metal-metal bonds. These are in the bin of the Z-type ligands because lithium here is just a Lewis acid. It would be this, we consider it to just play that role.
I guess that would also get us over 18. So if it's 6 from the olefins, then it's 18 overall.
Okay. So these Z-type interactions, the Lewis acid does not bring any electrons to the party, so we don't count those in terms of the overall electron count. Very good. Any questions on that?
What are the properties of that type of complex?
What would you expect them to be? Highly reactive. I think it can promote Kumada. So this complex was known from the 1970s. That's the first citation shown here, developed at the Max Planck Institute, and then cleverly utilized a couple decades later by Pep Cornea's group. And it can do room temperature, I think Kumada couplings at minus 78 degrees. And there's an interesting point that we'll get back to. Some people don't like this -2 oxidation state at nickel, and they would prefer to draw this interaction not as I have it drawn as an olefin interaction, but instead as a metallocyclopropane. And there you can convince yourself what I'm saying is right, or you can not believe me, but then if you do this counting, you'll get to nickel 0 species, so you don't have to invoke this negative oxidation state if you don't wish to. And often metal olefin bonds, depending on how electron rich they are, can be on this continuum of metal olefin versus metallocyclopropane. So for the, let me just redraw this the way that we had it, so that if you are looking back on your notes, it's not confusing. Super, Alex. Any questions on that? Come on.
Do you know if the cyclooctadiene ligands are equivalent by NMR?
Oh, that's a good question. Off the top of my head, I don't remember. I think in solution state, I guess my vague memory is in solution state, they are equivalent, but in solid state, obviously they're not. There might even be temperature dependence. So let me, that's a great question. Let me check on that, and maybe you and I can discuss offline. As you know, sometimes also these types of NMRs can be broad and a little bit difficult to interpret. Okay, so let's now close out this discussion by considering some special cases, which are cationic ligands. So they can donate electrons, but they also bring with them charge. And that will bring us to problem of the day, number 1 for the day 3 handout. Which considers this ligand NO, which is common in coordination chemistry. And there are 2 flavors by which NO ligands can coordinate to metals. Linear, which is the most common. So if you are not sure and you just see a molecular formula with NO, then you can assume it's linear. And then the other form, which is bent. And these have actually different coordination properties and different consequences in terms of electron counting. But I think it's actually this is one of these cases where you can learn the rule without thinking about it, and then you will, every time you'll learn it and you'll forget it, and you'll learn it and you'll forget it. Or you can just take 30 seconds to think about it, and then you'll remember it forever. So that's what I want you to do, is to take 30 seconds and think about it. I'll give you a hint, and actually the question gives you a hint, which is that in one case, the NO ligand is an anionic traditional X-type ligand. And the other, it's actually a cationic ligand. So it donates 2 electrons, but it's charged. And based on the Lewis dot structure, and in particular, the hybridization at nitrogen, predict which is which. And so the way to do that, I've tried to kind of set it up here, is just essentially break. So I've tried to set this up here to help you, which is just break these bonds and then consider the Lewis dot structure. So it's all in the hybridization at nitrogen. Okay, what do you think there, Elan, for both of these? Okay, so let's go ahead and break this. So what did you get for the Lewis dot structure here?
Just like let us see the constant.
something like this. And then you said it was overall plus. So again, the key here is all about the hybridization at nitrogen. So SP, SP. And then to get to a closed shell species, you have this as plus, and then presumably you got to the opposite case in the bent NO situation and concluded that was anionic. Is that right? Okay, so then when we see these in coordination complexes, we'll know that the linear NO is effectively a special case of L-type ligand. It will donate 2 electrons, but bring with it +1 charge. And the bent NO is effectively a typical X-type ligand, 2 electron donor, but -1 charge. Okay, very good. Any questions on that? And as a reminder, there's a handout that has a broader array of ligands than those we've covered today and shows how to electron count for them. So I'd encourage you to take a look at that handout. And then before closing out the discussion, we'll just consider one more interesting series of complexes, of ligands, which are is this isolobal aromatic series going from CP. So as you remember, the formula for aromaticity is what? When you made eye contact. So I'll torture you. 4N + 2. And so, just like when things aren't coordinated to metals, when they are coordinated to metals, ligands are coordinated to metals, they like to be aromatic when they can. And so you have this series that in all cases contains 6 electrons going from CP anion to neutral benzene to tropylium. Different numbers of carbon atoms in the cycle, but electronically equivalent. We've already seen that CP is overall -1. Benzene we would consider and is a 2LX ligand. Benzene is neutral and is a 3L ligand, and then the tropylium here is going to be what? It will be 3L, but of this weird subtype that brings with it a plus charge. Okay, any questions on electron counting? We'll get, again, I think there's no substitute in electron counting for just doing lots and lots of examples and simple examples and exotic examples and getting practice, which you'll have plenty of chance to do on the homework. As well as throughout the class. So if you're thinking it's a little bit still not super comfortable, then please stick with us, and we'll try to get enough examples here where it starts to become more and more natural. Okay, so for the remainder of the class today, we'll discuss the next phase of structure and bonding, starting with a discussion of periodic trends. And so this part I'll go through quickly, and I'll highlight that there's a handout available that highlights a lot of these periodic trends, with essentially screenshots directly of tables from textbooks. But I'll just recapitulate some of the key trends here, so you have all of the information in one place. And so some of the key points I'd like to emphasize here are that in terms of thinking about the periodic table in the main group, we're used to the trends being, generally nicely continuous as you go left to right and up and down. And that is not necessarily the case in the transition series. And so it is best when making arguments based on periodic trends to consider a particular series of complexes. And so the more localized your comparisons are, the more reliable the periodic trends will predict structure and reactivity. Another key point to make here is that, as we've seen already in terms of the atomic orbital energies, the trends of properties when you compare element to element can be different when you're comparing complexes versus the naked metal ions. Okay, so those are some of the disclaimers here. So first, let's consider ionization potential, which is just essentially a measurement of how easy or difficult it is to remove a electron from the high energy filled d orbital. And so do we expect that we would have, in terms going left to right or right to left in the periodic table, do we expect, which do we expect to have increasing ionization potential? Wenji, you sighed uncomfortably. What do you think?
Because if you go towards the right of the table, it's getting more difficult to ionize.
Okay, so increasing ionization potential going left to right. So we've already talked about some of the electronegativity trends. We know that when we go up and right in the periodic table, atoms are more electronegative, and electronegativity is a reflection of how tightly those atoms like to hold on to electrons. So that I think follows somewhat logically. We also know that in general, it's easier to, well, I don't want to get ahead of myself. I almost gave a spoiler for one of the next questions. So I'll leave it at that. So let's consider this case then of oxidation. I'll just stay with you, Wenji, since you, this is just a direct consequence of what you just said. So if you had to choose what was going to be easier to oxidize, zirconium-2 or palladium-2, what would you choose?
More readily giving out electrons, so zirconium-2 is easier to be oxidized.
And then two equivalent ways to phrase that would be to say the zirconium-2 is more electron rich or more basic. Great. So now when we're going up and down columns, things are a little bit more complex. And this is what I said, that there are some added complexities in the transition series that you don't necessarily find in the main group. But one thing that we can say is that the formation of high oxidation state species, so which we define as something +3 or higher, is easier for third row metals than, I won't say harder, I'll say more difficult, because harder can mean something else. Easier for third row than for first row. And so we can consider an example from the series that we were just in. So nickel, for example, in the +4 oxidation state is quite rare. And when you have a well-defined nickel 4 complex, then you publish it in a good journal because it's notable. Whereas platinum +4 complexes are quite common and have been known for a long time. Okay, now let's consider size. And so what do we think about size here? Maybe I'll take ask for a volunteer. Anthony, as you go first row, second row, third row, bigger, smaller, the same?
Anthony's not here.
Oh, okay. I'll ask for another volunteer. All right, Shenghua, what do you think?
The atom radii gets larger as you go down.
Okay, so that is true from the first to the second row. What about second to third row?
It gets smaller instead, or it's roughly similar.
It's roughly similar, exactly. Kind of a trick question.
So are you saying going down the column? Of the row column thing is confusing to it. Are we talking about down a group or down a row?
Down the row.
That's a
No,
column.
it's like you
Columns
go
going
vertical.
down, right? I'm just confused, sorry.
And like the first row is smaller than the second row. So you're moving downwards, but we're talking about the entire row basically.
We're describing two things at once now. Sorry, Kiri, can you are we talking about nickel versus platinum and palladium, or are we talking about copper
Yes.
versus?
Yeah. So when we refer to the first row metals, we're talking about cobalt, nickel, iron, not in that order.
Because the trend is down the column. I'm just thinking of like linear algebra. I got it though.
Right. We're comparing row to row, but the trend ends up being a trend that is a columnar trend. Yes. Sorry. Okay, and so I think intuitively this first part I think is we're probably comfortable with from the main group because we know that a higher principal quantum number of valence orbitals leads to larger size, higher energy orbitals involved. But this other one, trend is a little different and somewhat unique to the transition series. And it stems from two factors, the first of which is believed to be dominant, which is called the lanthanide contraction. And, which is a result of the nuclear charges of third row being much higher than the second row. So this is because as you go to higher and higher principal quantum number, the orbitals become more and more diffuse. And as you layer more and more diffuse orbitals on, the effective charge of the nucleus is felt more because there aren't as many electrons packed efficiently around the core. And so that's what we say is the effective nuclear charge becomes higher. And then a secondary effect is called a relativistic effects. which are that as you get to higher and higher orbital energies, you need to consider the particle wave duality of the electrons that are involved. And at higher and higher energies, the electrons start to approach the speed of light. And based on the principle of relativity, thus become heavier and give a smaller overall size. So that's maybe a little bit too much of the gory details, but I want you to have a sense of where this periodic trend comes from, because it ultimately derives from first principles that you've all seen before in Gen Chem. Okay, so let's consider another periodic trend here as it pertains to size. So for complexes of group 4 to 7 with the same charge and oxidation state, size then will decrease as you go left to right on the periodic table. So you have to add several caveats. Again, you're comparing now within a similar group and at same oxidation state, but then you can say that size decreases left to right, and that's just a direct consequence of having higher nuclear charge. Okay, so now let's consider, I think, one of the perhaps most important periodic trends that you'll see reflected again and again throughout the class, which is metal ligand bond strength. And this trend is very clear that first row metals form the weakest bond. First row metals form the weakest bond to carbon, and third row metals form the strongest bond to carbon, with second row being intermediate. And one note here that is perhaps of interest is that this trend is actually the opposite of the trend in the main group. For example, bonds carbon chlorine to carbon iodine, the latter is weaker than the former. So what is the origin of this then in the transition metal series that is distinct? And this ultimately comes down to typically what people will say in somewhat hand-wavy format, and we'll try to unpack this a little bit, is that there's better spatial spatial overlap of the orbitals involved in bonding in the second row and the third row compared to in the first row. And I think in the previous time I've taught this class, somebody asked me to unpack this and the discussion got a little bit confusing. So I've tried to clarify this discussion this time around. Hopefully you find it clarifying. And if you don't, then I'm sorry I made things worse, but I promise I tried to make them better. So I'll direct you to this article, which I think has, despite being in the Journal of Computational Chemistry, has a pretty intuitive explanation for this trend and the underlying origins. But we can see that this falls out really of considering the atomic orbitals that are involved in bonding here. So let's go back now and kind of have a quick Gen Chem review. So when we're talking about atomic orbitals, we know that we have two principal quantum numbers. So for any given orbital, N and L, the N denotes the principal quantum number, and L denotes the angular quantum number. And so for so let's consider the case of 4d orbital. Then the principal quantum number here is n equals 4. The angular quantum number L is equal to 2. And then let's fill in these blanks, and then we will jump to problem of the day number 2. So the total number of nodes for a given orbital NL is what? So 1s orbital we know has 0 nodes. Just the general formula. So we know, for example, 1s orbital has 0 nodes. And then n minus 1, is that what you said? But then how does that, oh, I see, n minus 1, yeah, okay. And then the number of angular nodes is what? L, okay. Okay, so now let's use this to background knowledge to consider problem of the day number 2, which I think can be fast if it clicks right away, but might not be fast if it doesn't click right away, which is that it asks you to consider a 4D orbital. So this is relevant to this discussion because we're talking about bonding to 3D orbital, 4D orbital, 5D orbitals. So consider a 4D orbital as a representative case and draw the shape of a 3D orbital. And if it's easy for you, I would just draw the projection in 2 dimensions because 3 dimension might be more complicated. So take a minute to think about this, compare with your neighbor. Think about the number of angular nodes and think about the number of radial nodes. So the total number of nodes, as Pranali said, is n equals 1, and that's also equal to the number of angular plus number of radial nodes. And if this is review for you from Gen Chem, then you should get it very fast. And if you haven't thought about this in forever, then maybe it will take longer. Either is fine. Okay, so let's, I'll just start kind of working this as you're thinking it through. So you're not. Now I'm very nervous of how this recording went when I was doing it by myself. So the total number of nodes n minus 1, and then it's equal to the number of angular nodes plus radial nodes, and the number of angular nodes comes directly from L. So let's plug into this formula. So Pranali said n minus 1, so the total number of nodes, in this case, we have principal quantum number of 4, n minus 1 will be 3. The angular quantum number is 2, so the number of angular nodes is 2, radial nodes 1, then. And so, as I said, I'm just going to draw this as a 2D projection to make my life simple and not create embarrassment as I try to draw it in 3 dimensions. So we have 2 angular nodes. I would ask for volunteer, but I'm actually not sure how it would work for you to describe what I'm drawing. So we have 2 angular nodes, that's the vertical and horizontal line, and then the radial node, which is the circle here. And then we just fill in electron density, and I'll do it here. Using the phases that we know exist in the sorry, this is an elegant structure. I would encourage you if this is, I'm trying my best, but if this is like really unclear to you, then just you can look online for as we're doing this, even on your phone, of the structure of the shape of a 4D orbital, and this will maybe become. So this is a 2D projection of a 4D orbital. And the key point and the reason I want to take time in class to draw this out is the key point is that the presence of radial nodes in the 4D and 5D orbitals effectively pushes a lot of the orbital density away from the nucleus. And that pushes the orbitals into a spatial orientation where they can form better overlap with the orbitals involved in bonding from the ligand. So let's take a closer look at that with this diagram over here. So now we're considering something that looks more like the case in a 3D orbital, specifically the DZ squared orbital. And you can see that in the 3D level, this core shell of S and P orbitals effectively crowds the 3D orbital, preventing a good level of orbital overlap from the incoming filled orbital of the ligand. And the ligand, as it's trying to form orbital overlap with the DZ squared orbital, in this case, experiences Pauli repulsion, destabilizing that interaction. So again, it's a trend. People will often, I think, use this throwaway statement of orbital overlap, but I want to unpack that a little bit more because this really underlies a lot of what we'll see later in terms of elementary reactivity and catalysis. Are there any questions on that? I went through it somewhat quickly, but hopefully it's clear. And again, if this drawing is confusing to you, just please look up the 4D orbital. Okay, one concept that we'll cover quickly, and in some ways it's sort of like kind of like an orphan topic that doesn't really fit anywhere. So we'll just cover it, and then you'll be familiar with this nomenclature, and we'll encounter it a couple times in class. You'll see it when you're reading papers, et cetera. And this is the idea of hard-soft acid-base theory. In many ways, I think this is quite intuitive. It defines given atoms as hard or soft based on how large or small they are and how densely charged they are versus how diffuse their orbitals are. So things that are hard are small, densely charged, and have orbitals that are not, and have electrons that are non-polarizable. So in the context of the transition series, first row metals are generally viewed as hard metals. And the opposite is true of soft elements. So these are atoms that are large, that are diffusely charged, and that have highly polarizable electron clouds. And we consider second and third row metals or metals containing multiple bonds to be soft metals. And then you can imagine the types of ligands that we categorize as hard versus soft. So things like fluoride, alkoxide, those are hard ligands. Things like sulfides, phosphines, those are soft ligands. And the upshot of hard-soft acid-base theory is that soft-soft interactions are stable, hard interactions are stable, but hard-soft interactions typically lead to less efficient bonding. And this really ultimately stems from just how how much orbital overlap you have when you're forming bonds between the metal and the ligand. Okay, so now, as systematically as we can, we'll try to build up this understanding of how we go from molecular formula to being able to anticipate what a three-dimensional structure might look like. And we'll do this through a series of theories of varying levels of sophistication. The first and least sophisticated is something you've already covered in Gen Chem, which is VSEPR theory, valence shell electron pair repulsion. And this basically is the same treatment that you have and you've learned in main group elements, which is that for a given coordination number or around a metal, there are only so many possible geometries that lead to the valence shell electrons being maximally apart from one another. So this is essentially VSEPR theory, is thinking about the ligands as electron pairs and trying to minimize charge and splaying the ligands out in space around a sphere to minimize electrostatic repulsion. And so just to go through this very quickly, in two coordinate species, there are two flavors. You could have linear coordination mode or bent coordination mode. Linear is observed for this gold dicyanide complex as well as copper 2 chloride. And then you can have a bent geometry, which is effectively isostructural to water, and that's seen in tin dichloride as one example. In the three coordinate series, you can have three geometries: trigonal planar, pyramidal, and T-shape, with the latter two being more specialized, although not so specialized that you don't ever encounter them. So here's an example from the recent literature, one from Pat Holland's group. And Pat prepared and isolated and characterized this interesting nickel 1 complex. Which we previously encountered a nickel 1 in one of the problems today, so we know that's D9. And with this NAC-NAC type ligand, which is a relative of the more familiar ACAC ligand, where you have nitrogen instead of oxygens here, and bulky aryl groups, the earlier dip group. Actually, this nickel carbonyl complex was found to be T-shaped. I think the next couple are the ones that you'll encounter most commonly in this class. So 4 coordinate species can have 2 favorable geometries: square planar, tetrahedral, and then distorted versions of those geometries. 5 coordinate can form trigonal pyramidal and square pyramidal, again using nomenclature here from Pythagorean geometry, and then 6 coordinate will be octahedral. And actually you can push this further. In our lab, we've worked with some 7 coordinate tungsten complexes, which have a very unusual coordination geometries, but these are, I would bin as more exotic, so we won't cover those in class in the interest of time. So these are some of the more familiar ones. So let me give a couple concrete examples of complexes that adopt these geometries. So for the square planar, we have rhodium 1 complex shown here, which some in the audience might know the name of. I didn't even finish the molecular formula, Lindsay, when you already knew that. Good. Wilkinson's catalyst, tetrahedral. So these are some 10 metal examples. Palladium tetrakis, triphenylphosphine, chloride, and 0 respectively. And then octahedral, we already said that Werner complexes are octahedral. Carbonyl is an example of a carbonyl complex, it's octahedral, and iron, 6 water molecules, hexa aqua. But VSCPR theory, the strength of it is that it's very intuitive to understand and simple. The weakness is that it doesn't understand a lot of the most interesting features that organometallic complexes we know exhibit. And so VSCPR cannot account for why organometallic complexes exhibit magnetism, why they're colored. And so there was a need for a more powerful theory that can inform on not just three-dimensional structure, but also on valence electronic structure. And the first one to come online that answered a lot of these lingering questions was called crystal field theory, developed in the 1930s. And if you're thinking about the timeline here and the history of organometallic chemistry, you'll note here that the development of crystal field theory actually precedes the discovery of some of the most important complexes in organometallic chemistry history. And the crux of crystal field theory is that it describes the breaking of orbital state degeneracies, electronic orbital state degeneracies, through application of a static electric field. So what this does, in essence, is it takes the ligands that are coordinated around the metal, so let's say octahedral, and considers all of them as point charges. And as you move these point charges from infinity towards the metal, some of the orbitals, depending on their shape and orientation, become higher in energy and some become lower in energy. And so, we know in general, and so the key point here is that this is, already you can note that this is an approximation because it's considering all the ligands as point charges, which we know the bonding is in fact more complicated than that. The attractive interaction of these point charges of the metal, I think, falls out of the fact that metals in general are positively charged, sometimes formally positively charged, depending on their oxidation state, and that the ligands involved in coordination are negatively charged. So as those negatively charged ligands approach the metal center, then the quote non-bonding electrons centered on the metal, they change their energies based on this applied electric field. And the effect on some d orbitals is more pronounced than others, as we'll see. And so this leads to breaking of the degeneracy. So the point charges that directly run into specific d orbitals get the higher energy, and those d orbitals that avoid these point charges can actually go to lower energy. And so the overall splitting energy, which we define as the amount that the d orbitals, the magnitude of by which the d orbitals are affected by the applied ligand field, depend on the oxidation state of the metal, as well as the binding strength, the field strength of the ligands involved. So higher oxidation state metals give higher splitting energy, higher field ligands also give higher splitting. Okay, so just as one example, if we consider the d orbitals here, which I drew out in advance to avoid embarrassment, and we apply an octahedral ligand field here, then what we're doing is taking these 6 point charges, moving them towards the center, and asking which orbitals experience the most repulsion to these point charges. And so one of the things you can appreciate immediately from this octahedral field is that these point charges, as we move them in, they will directly run into the dz squared orbital and the dz dx squared minus y squared orbitals, whereas the other three orbitals, they more or less miss these point charges as we apply this field. Okay, so let's consider this now, what the actual consequences of this ligand field, the octahedral ligand field are. So in the absence of any applied field, we know that these 5 d orbitals are degenerate. Then we can apply a spherical field, which is called a barycenter. And again, because the applied field here is spherical, all of the orbitals involved experience it the same way. And so they all go to higher energy. But then if we instead apply an octahedral field, I just gave you a preview of this, we saw that the dz squared and dx squared minus y squared orbitals go to high energy, whereas the other 3 orbitals are less affected. And so this overall difference I want to redraw this to avoid confusion. So the overall difference now between these orbital energies is the splitting energy, which we denote by delta. And then if you can subdivide this further and see that those that go to higher energy, those orbitals that go to higher energy, 0.6 multiplier. Those that go to lower energy have 0.4 multiplier. And we already saw that octahedral geometry is common for D6 metals like the Werner complexes. So then we can go ahead and fill those orbitals in with, consider a D6 case, and we see they nicely fit all in the lower orbitals that have predominantly dx squared, dxy, dyz, and dxc character. And so every different coordination geometry has a different ligand field associated with it, and that has different effects to the d orbitals involved. And so we can walk through multiple cases here. And I think when I was first learning this, I found it sort of quite unintuitive about what the actual energy levels of the orbitals involved for different molecular geometries look like. But I think after you've done a couple, and started getting the hang of it, it starts to become a little bit more intuitive. And in the previous class, I had a question which is interesting, which is what does this splitting energy actually translate to in terms of things that we're more familiar with as chemists? And so you can do a quick back of the envelope calculation and know that a lot of organometallic complexes, including the Werner complex we covered, or coordination complexes in general, absorb visible light, and absorbing visible light, that's creating excitation from the unfilled orbital to the filled orbital. And then you can do a back of the envelope and see what that wavelength of light is equivalent to in terms of electron volts or kcals per mole, and that's sketched out here if you're interested in that. Okay, now we can consider just have a few more minutes here. Let's consider these 2 examples quickly, and then that would be a good place to stop. So we can also consider now a tetrahedral ligand field, and in this case, the orbitals that run into the point charges of a tetrahedral field are the opposite of those that run into the point charge of the octahedral field. So in this case, the dxy, dyz, and dxz orbital go to higher energy, and the dz squared, dx squared minus y squared go to lower energy. And you see the overall magnitude of the effect of splitting here is lower than in the octahedral case. Why is that? Because if you think back to this orbital depiction, a tetrahedral ligand field does not directly run into any of the orbitals the same way that an octahedral field runs into the dz squared and dx squared minus y squared orbitals. It sort of, in any orientation, it kind of avoids directly running into those ligands. And that's why the effect of the overall splitting energy is lower. And that's why oftentimes tetrahedral complexes can be high spin, and we'll unpack what that means later in class. But the overall difference between these two energy levels is lower, which means that as you're filling in orbitals, this higher energy orbital can get filled in. So this tetrahedral geometry is common for D0, D5, and D10. And we just saw examples of D0 and D10 as we were going through that table earlier. And so this point here is alluding to what we mean by high spin versus low spin, which is as you're filling in energies, let's say you have a D5 complex and you're going through and you're filling in electrons. You fill in the first two like this, and then you have a choice. Do you fill in these orbitals or do you fill in these orbitals? And this is a consequence of how large the splitting energy is. So this case was called D5 low spin. Okay, let's, we just have a minute here. So let's now consider the square planar case. And then here you can recognize that if you apply a square planar field and, by convention, the z-axis is the axis that you define as the highest symmetry axis. So a square planar geometry, the metal ligand bonds exist in the XY plane. So then you can appreciate that as you apply a square planar ligand field, the ligands that are, the orbitals that are destabilized most are the dx squared minus y squared, followed by the dxy, and then dz squared, dxy, and dyz. This is common for D8 metals. So if we can do that, fill in what that would look like. And because this is most commonly observed with D8 metals, that's why the splitting energy in this case is defined as this difference here. In principle, you could define it as any of these, but it's defined this way because it's so common for D8 metals. Okay, let's quickly, as we close things out, just consider problem of the day number, or this isn't a problem of the day, but this is just an example. Okay, but so let me, just continue this. Oh, what did I do here? So we'll try to apply everything we've learned to predict the structure of a ligand exchange reaction that you've never seen before. So this ligand exchange reaction is treatment of palladium acetate with two equivalents of this. I'll give you a hint. This ligand here, and we can identify that it's a ligand. I mean, in principle, if you know nothing about this, the first question you're asking is, I've never seen this compound before. And I need to ask myself, what properties does it have? Is it an oxidant? Is it a reductant? Or is it something that's going to coordinate to the metal but not change the metal's oxidation state? In this case, we would look at this bioether containing carboxylic acid and say it's not particularly oxidizing, it's not particularly reducing, it's most likely going to disengage in ligand exchange. So what could a potential structure look like? Well, I'll take a quick tangent there and ask if anyone in the audience knows the actual preferred 3D structure of palladium acetate. Maybe somebody from Jin's lab handle this every day, and I see they're all avoiding eye contact. Annabelle, what is the actual 3D structure of palladium acetate? Okay, trimeric, beautiful. Try to draw this somewhat quickly, but still clearly. I don't know if I will succeed. So palladium acetate, and the references here on the left, you can find the first synthesis from Wilkinson, 1965, and then the structural elucidation 5 years later. It can exist in several forms, actually. It's kind of complicated, but the most common, with the brick red solid that we're familiar with, is this trimeric form, where each acetate, each acetate bridges two palladiums. I hope I didn't make too much of a mess of this, confuse you. So the only point I want to make here is that we've, most of us at some point in our career will work with palladium acetate, and many chemists don't actually know what its structure is. And it's trimeric typically when you find it in this brick dust form. And the important point here is that if you quickly do the oxidation state determination, you see palladium is +2, and palladium prefers to be square planar, and that's why ultimately why it assembles into this trimeric form. Okay, so now a ligand exchange event. Dylan, why don't you predict what a possible product is, or if you have multiple products in mind, walk us through what you're thinking.
I was kind of thinking we would have 2 of the ligands around palladium with oxygen binding and sulfur binding.
Okay. And walk us through your thinking there. Or binding to it.
The palladium acetate that it has like 4 open sites, I guess, that you could have coordination. That's just when I first looked at the ligand, that's what popped out to me. I don't know if that makes sense.
And what do you prefer? Do you prefer this stereochemistry, or when you sketched it out, or this stereochemistry?
Sketched out the top one, but I kind of like the bottom one a little bit better.
And how would you go about determining which is formed in the flask?
Test polarity.
Polarity. Which would you expect? How would you test polarity?
I don't exactly know, but
You have to force to get the other, you have to compare it to something, right?
That's the problem. You don't have a reference to compare it to. But you're right, this would have a stronger molecular dipole.
You just hand wave the trans effect and say that the like ligands are going to be opposite each other.
You could, but then you could be wrong. I think the most direct and unambiguous way to do it is probably so obvious nobody's saying it. So Shenghua, our resident expert, how would you make this determination?
Frederick.
You would try to grow a single crystal. And even if you crystallize the mixture, you'll probably get one out, and then you can take that pure sample and assign by NMR which it is. And in fact, actually, these are indeed isolated as a 2-to-1 mixture in this experiment. In both cases, palladium is square planar, so we're already learning something in class. We're learning not to draw tetrahedral palladium 2, and this is important that, you know, like if you have tetrahedral geometry, you don't have opportunity for this type of stereo isomerism.
Is the 2-to-1 favoring the cis or the trans?
I believe the cis is favored here, which is somewhat surprising to me because I would have guessed the two relatively bulky sulfurs would prefer to orient trans to one another, but sometimes there can be more complicated effects at play. Okay, so lastly, I'll just, this specific example, we'll close out here. The specific example was from the lab of our chemist of the day. I don't know if anyone would recognize her. This is Tati. Tati is her nickname, but that's also what she goes by professionally. And that's Ibanez. Maybe those in Jin's group would be familiar with her research because she's an active in CH activation and she works at the University of Amsterdam. And did her training PhD with at the UAM, Universidad Autónoma de Madrid, with professors Morano and Maestro, and then was visiting student Scott Miller, postdoc with Ben Feringa, and then has been an independent professor at the University of Amsterdam since 2015. So we'll close things off here, pick it up with spectrochemical series, and then wrap up the history, structure, and bonding part of that. So thanks, everybody. See you Thursday.